One of the most important applications of heat transfer is the prediction and modeling of how fluids transfer heat between each other. In particular, how we can design or optimize devices that allow heat to be transferred as optimally as possible between a hot fluid and a cold fluid. Now, we had seen and talked about this kind of device before. We had called it a heat exchanger. And so the thing that I want to do now is go back to discussing these devices, but not necessarily from the perspective of just showing you one and telling you here's what the design is, but more from the perspective of describing the parameters that people use to characterize these devices and how we can get to those parameters using the simple models of heat transfer that we've created or discussed so far. So the simplest way to describe a heat exchanger is just some kind of device, a pipe with a metal flange in the middle, where we have hot liquid flowing in one direction with a mass flow rate m.h and all of the material properties that you would expect such a fluid to have, a density, a specific heat capacity, so on and so forth. And then you would have a cold fluid, which is separated from the hot fluid by the, little flange, or whatever you want to call it, with a different mass flow and a different specific heat capacity and a different density. And the characteristics of the way that these two fluids flow inside of the system, the geometry associated with this separating barrier, the geometry of the pipe or duct that contains them, all of this stuff affects the heat transfer that occurs between the hot liquid and the cold liquid, okay? In addition, something as simple as altering the directions in which these liquids flow can significantly impact how effective the heat transfer between those two liquids is in this system. And so I want you to think for the moment, for the rest of the lecture, while you hear me drone on and on about parameters or whatever, I want you to think about the following question, which is it better for the liquids to be flowing in the same direction, so for the hot liquid to go this way and the cold liquid to go that way, or is it better for the hot liquid to flow this way and the cold liquid to flow that way, right? So in opposite directions. So keep that in your head while I talk. Overall, however, if you think about trying to model this system in a simple way, it really just looks like we have two coupled internal flow problems, right? This is the flow of a liquid through a duct. This is the flow of a liquid through a duct. These things are exchanging heat, right? The amount of heat that goes from the hot liquid into this, separating barrier has to be the same as the amount that's going from the barrier to the cold liquid, assuming that this heat exchanger is operating in steady state. And so when we make those sorts of assumptions, when we try to simplify the way that we analyze the system as much as possible, it turns out that understanding these systems is relatively straightforward, at least conceptually. So what is going on here? Well, we know that there's temperature differences that are going to occur from the inlet or the outlet for both liquids, whatever those temperature differences may be, right? We know that the point, just like as we had seen with internal flow, the idea is that the liquid changes temperature, and so therefore the temperature of the liquid throughout the duct in either case is not uniform, okay? Nevertheless, we can try to take a look, we can try to figure out whether or not we can create some kind of model for the net heat transfer rate that's happening through this heat exchanger by postulating the idea that this system follows something that looks like a thermal circuit law, right? That the net heat transfer rate from the hot liquid to the cold liquid times some thermal resistance is equal to a difference in temperatures. Now, this is the tricky part, right? Because since we know that the temperature of the liquid changes from the inlet to the outlet in both cases, there isn't really like an obvious delta T that we can use. But I don't want to focus on this for now. I want to focus on this. And the idea is that we want to construct this thermal resistance to be as similar as possible to all of the other kind of thermal resistances, or at least the conceptually we use the same building blocks to create this proportionality constant between Q and the delta T. And then we take all of the complexity and we shove it onto this delta T. Okay, so let's try it out. So what if I tried to create a thermal circuit between the hot liquid and the cold liquid, what would I wind up getting? Well, let's suppose that we have a node that represents the hot liquid. So I'm just going to call it H. We don't necessarily have a specific temperature for it. Again, we haven't defined what this is yet, but we're just playing this by ear and seeing where we go. And if we say that this node is the hot liquid, this hot liquid is in contact with this solid barrier, which by extension means that there has to be a convective thermal resistance that occurs between the hot liquid and the plate. So I can draw one thermal resistance right here that represents the hot liquid, right? And which is a convective thermal resistance. It has 1 over H, 1 over H hot times the surface area of this connecting element. Now I put the subscript hot down here because the whole point is supposed to be that the heat transfer coefficient in the hot liquid, or between the hot liquid and the plate, is not necessarily the same as the heat transfer coefficient between the cold liquid and the plate, okay? So we have to be very careful about that. But the convective resistance is nevertheless written in the exact same way. All right, so sorry if this looks a little bit bungled, but hopefully this is a bit more readable. Okay, so we have this. Now we have a conductive thermal resistance. A conductive thermal resistance that represents the the separating element. Okay, and now this one, I don't want to write an explicit expression for, simply because of the fact that it depends heavily, right, on the geometry. So in this example, it looks like we have something that's planar. You can imagine that if we had a set of concentric tubes, the separating element might be cylindrical. But you can also imagine, as we saw in the example for a heat exchanger before, that the separating element or elements have such an extremely complex dividing geometry that we can't really use expressions for thermal resistances, conductive thermal resistances that we've seen before. But nevertheless, this is a conductive thermal resistance. Whatever that number is, whatever the goofy expression is, we know that there's a shape factor associated with it, and that therefore we can find a conductive thermal resistance. And then, of course, we also have a convective thermal resistance that happens between the separating element and the cold liquid. And that one has precisely the expression that you might think, right? It's just the 1 over H times AS, where the H is on the cold side. So H cold, if you want to think about it that way. And then this connects down to the cold liquid. And so you can imagine, right, that we can construct this sort of hypothetical thermal circuit for these sorts of heat exchangers. Now, there's one practical thing that I think is worth mentioning about the way that heat exchangers behave. One of the key engineering problems that happen whenever you're dealing with heat exchanger is a process called fouling. And what fouling is just, whenever you have some sort of liquid, that liquid usually tends to be impure. It's got all kinds of weird stuff, in it. And sometimes that weird stuff will either interact physically or chemically with the separating element and start to build up on the surface of the separating element. This is particularly true, for example, whenever you're dealing with like biological liquids. So this is a common thing that happens in, say, plumbing. And by the accumulation of that matter, whatever it is, it causes the separating element to kind of be a combo of the original object and this kind of gunk that starts to build up or foul the original surface, right? And because it's extra solid, right, because it's extra matter, this conductive thermal resistance starts to grow, which impedes, optimal heat transfer. So the way that we model the effect of fouling on heat exchangers tends to be by defining some kind of what's usually referred to as an R value or a thermal insolence that tells us something that's proportional to the thermal resistance that's being caused by that fouling effect. So most of the time what you'll see is that people will define this thermal insolence R double prime, and they'll say that this is, I guess you could say, some sort of material property associated with the fouling effect that is equal to the thermal resistance times the surface area over which that fouling effect is taking place. Okay, so this is almost sort of like a thermal resistance times surface area. And so people will model, the effect of fouling as having this sort of relationship where the R double prime is a material property of the fouling object or of the fouling process. And then of course the surface area is just geometric. And then you would insert this thermal resistance right here into the thermal circuit. All right, so that's usually how fouling tends to be modeled. All right. That answers the question about what this thermal resistance should be, at least conceptually, from the perspective of what we know how to model in these sorts of systems. But we don't necessarily know what this delta T is. And the answer of what this delta T should be, which can come from either a lengthy numerical derivation or a couple of approximations that we can do, none of which I think are too germane to what we're trying to do here, which is just to create an approximation. Right? This delta T is going to be a delta T that we used familiarly when we were considering pure internal flows. And that delta T is just the log mean temperature difference. Okay? Which will be defined in basically the same way, except that now we can't really use a differentiation between inlet and outlet, because this side of the heat exchanger is no longer necessarily just an inlet, right? This could be the inlet for the hot liquid, but the outlet for the cold liquid too. So what I like to do whenever I try to work on these sorts of problems is I like to say, well, why don't I just define this location to be 1? So this side of the heat exchanger is just 1. This side of the heat exchanger is 2. And it doesn't really matter which one I call 1 or 2. It's just, an easy way for me to keep track of things. And all I have to do here is just to say that, well, this delta TLM is just the difference in temperatures between the hot liquid and the cold liquid at point 2 minus the difference in temperatures between the hot and the cold liquid at point 1, and then divide by the logarithm of their ratio, just like we did before. Okay? So this is exactly the same formula, except that now rather than using outlet and inlet, we're using, 2 and 1. So what we want to do now is we want to try to see whether or not we can construct some other equations that will allow us to determine not just what the heat transfer through the system is, but a way to characterize this thermal resistance. Okay? So you would think that when we are considering the characterization of heat exchangers, when we write down a value that tells us how good or bad the heat exchanger is, you would think that the value that we would use is this R, this total thermal resistance. But it turns out that, engineers prefer not to use this total thermal resistance, even though it seems kind of intuitive to use it. They prefer to define this somewhat new quantity, which is often referred to as a U value. It has another name, and I won't spoil it, but you'll see what it is as we do this calculation. And all that this U value is, just like basically everything else in heat transfer, it is a proportionality constant. And it is defined in such a way that the heat transfer rate is equal to that U value times the surface area over which the heat transfer is taking place, multiplied by this delta TLM. And so you can see that there's a direct relationship between the U value and this total thermal resistance, which we can investigate, right? We can immediately figure out that R is equal to 1 over UAS. And so by observing this expression, right, that the total thermal resistance is equal to 1 over this U value times the surface area, you observe that this U is behaving like an effective heat transfer coefficient for the whole system, which is where its other name, which is the total or effective heat transfer coefficient, that's where the other name for the U value comes from, because this effectively behaves like we model the heat exchanger as having this one big, huge, combined thermal resistance, which is purely a convective thermal resistance with this heat transfer coefficient U, or effective heat transfer coefficient U. And so it has the same units as the standard heat transfer coefficient, all right? And so very often when you try to find tables or figures that characterize the behavior of a heat exchanger, you'll usually find this value U listed for them. So we have an equation for calculating, or at least approximating, the Q as a function of either a total thermal resistance or this effective heat transfer coefficient U. Are there other equations that we can use to find the heat transfer rate through the system? Of course. And we can find one right off the bat by recognizing the fact that this is an internal flow for both the hot and the cold liquid. And so that golden rule for internal flow still certainly applies. We can absolutely still say that the heat transfer that's happening from the hot liquid to the cold liquid can be characterized by m dot, let's say H, let's consider the hot liquid, that this heat transfer is equal to m dot H times CPH, right? The mass flow rate of the hot liquid times the specific heat capacity of the hot liquid, and then multiplied by the temperature of the hot liquid at the inlet minus the temperature of the hot liquid at the outlet. This is coming from the same exact kind of energy balance that we had talked about when we were dealing with internal flow, right? We see that energy leaves, thermal energy leaves the hot liquid. It has to leave via the process of heat exchange with the cold liquid. And so the heat transfer rate to the cold liquid from the hot liquid can be understood or determined only by looking at the change in the temperature of the hot liquid from the inlet to the outlet. We can do the exact same thing for the cold liquid. If we wanted to characterize what the heat going into the cold liquid was, then we could just define the same kind of expression, but for the cold liquid, using the cold mass flow rate and the cold specific heat capacity. And then now this time, multiplying by the temperature difference with a flip on the outlet and inlet, just because, again, the whole idea is that in this case, right, in order for this to be positive, we're considering it from the perspective of it leaving the hot liquid, and so we have to have this be a positive quantity, and in order for this to be a positive quantity, we have to perform the flip, right? Because now we're considering the heat that's going into the cold liquid. And so either of these expressions allow us to find what the heat transfer rate through the heat exchanger is without ever having to worry about anything involving total thermal resistances or even overall heat transfer coefficients. This is particularly useful because it gives you a mechanism to be able to determine what one of these temperatures is if you know three of them but you don't know the fourth, right? Because you set these equal to each other. As long as you know these, you're fine. And in fact, for the sake of convenience, one of the things that happens very often is that this combination of a mass flow rate and a specific heat capacity gets comboed in to a single term, which is usually called a heat capacity rate. Now, the notation for this differs between books, and people, I suppose. I personally prefer to use C with a dot on it, although you might find that some books will just have a capital C. And the reason that the dot shows up is, of course, because we're talking about a rate, okay? And so we define this thing called a heat capacity rate, which is just the product of a mass flow rate times a specific heat capacity. And so this product, if you look at it, right, this has units of, in the international system, kilograms per second. This has units of joules per kilogram degree Celsius or joules per kilogram Kelvin. And so ultimately, what you wind up getting is that in the international unit system, this thing has units of watts per degree Celsius or watts per degree Kelvin. And so this quantity actually winds up being a convenient shorthand for understanding the behavior of the system, because rarely ever in heat exchangers do we have to deal with one of them and not the other. Like, rarely do they ever show up independent of each other. The point is that we have these equations that we can use to characterize or find the Q. And then by extension, we can use these to find the overall heat transfer coefficient, or the R. Now, moving on, now that we have these expressions, are there other things, other parameters that are commonly used to describe the design of a heat exchanger? And the answer is yes. One such parameter is usually referred to as the effectiveness. We had seen the effectiveness, or the notion of an effectiveness, a little bit before when we talked about fins. And the idea with the effectiveness is that here we are defining it as the ratio of this Q, right, the actual heat transfer that occurs in this heat exchanger, and we're dividing it by a theoretical maximum. A theoretical maximum that I'm not necessarily going to derive in this lecture. The derivation process is a little bit messy, and it takes too much time for me to be able to justify putting you through it. But the whole point is that we can write down this theoretical maximum as the following. We know that in internal flows, right, this Q is the product of a heat capacity rate and a temperature difference. And so what is the largest temperature difference that we can possibly use in the analysis of this particular kind of problem? Like, what is the largest temperature difference that shows up anywhere in here? And although this is not a physical temperature difference, right, it's not a temperature difference that happens between overlapping pieces of liquid necessarily, okay? Nevertheless, it makes sense for us to consider, well, we want to use the temperature of the hot liquid before it actually starts exchanging heat or losing heat, right? That seems like it's going to be when the hot liquid is at the hottest. And we want to do the same for the cold liquid, right? Before it starts to receive heat, when the cold liquid is at its coldest. And so the temperature difference that we want to use is the temperature difference between the hot liquid at the inlet and the cold liquid at the inlet. The thing that's a little bit confusing, which requires the derivation, is the fact that the heat capacity rate that we're going to use here is not the maximum heat capacity rate in the system, it's actually the minimum. So we calculate based off of the mass flow rate and the specific heat capacities of the system. We figure out which one's largest and which one's the smallest, and then we take the smallest one and then we put it in here. As a sneak peek as to why this is the case, it's because if we tried to use the maximum heat transfer, the heat capacity rate, if we tried to put the maximum here, we'd technically be violating conservation of energy. But the proof of that is not something that I plan to discuss in this lecture. The point is that we can then use an understanding of what the Q through the heat exchanger is, an understanding of what this minimum heat capacity rate is, and this specific temperature difference to find an effectiveness, or, vice versa. Okay? So you'll see that the effectiveness of a heat exchanger is also something that's commonly listed as a specific parameter associated with its behavior. Another thing that shows up very often is called, colloquially, the NTU of a heat exchanger. And the NTU of a heat exchanger has a somewhat simple expression as a function of everything else that we've been talking about so far. And that expression is simply that the NTU of a heat exchanger is equal to its U value, right? Its effective heat transfer coefficient multiplied by the surface area over which the heat transfer takes place, divided once again by that minimum heat capacity rate, like the smallest heat capacity rate in the system out of the two, okay? And so this is just a way to reformat or repackage the information associated with, the overall heat transfer coefficient. And you may ask yourself, why do we bother doing this? Well, what units did the effectiveness have? What units does this NTU thing have, right? Remember that this has units of, an H, right, of watts per meter squared degree Celsius. This has units of meters squared. And this has the units of a heat capacity rate, which is watts per degree Celsius or watts per Kelvin. And so ultimately this thing winds up being a dimensionless parameter, just like the effectiveness is a dimensionless parameter. And so it turns out that for heat exchangers, we can do the exact same kind of dimensionless analysis or dimensional analysis to create experimental dimensionless parameters that have to be a function of each other. And from the perspective of heat exchangers, this NTU is almost always referred to as being explicitly a function of the effectiveness, and more often than not, as a function of the ratio of the heat capacity rates. So you take the minimum heat capacity rate and then the maximum one, divide them, and then of course you have a dimensionless ratio, right? And the idea is that the NTU of a heat exchanger is entirely a function of the effectiveness and this ratio, all right? And so if I wanted to test out the NTU, if I wanted to characterize a heat exchanger experimentally, we use NTUs and effectivenesses and heat capacity rate ratios because we can set up a simplification of the experimental process in the same way that we did for every other convective analysis that we've done so far. So kind of cool, kind of convenient. And then you can imagine that for different kinds of heat exchangers, you'll find different expressions for this, different correlations that tell you what the NTU is as a function of the effectiveness in this ratio. Similarly, of course, you can always try to do it backwards. You can always say, well, I want to find the effectiveness of my heat exchanger. And I can say, well, that's a function of the NTU and the heat capacity rate ratio. Doesn't really matter, right? And so overall, this happens. And so whenever you work with exercises, which we'll get to, very often you'll have to deal with this. Now, why is it that we have to set up a dimensionless analysis for something that seems as simple as a heat exchanger? Well, remember what we talked about when it came to enhancing the design of devices that transfer heat from one object to another. We have to maximize the surface area. And in maximizing the surface area over which the heat transfer takes place, we create extraordinarily complex geometries that lead us to try to struggle with understanding exactly what tools we can use to describe, the total thermal resistance or something like that, right? Like the effective heat transfer coefficient of the heat exchanger. So what happens? Well, as an example of the kinds of heat exchangers that you might see in practice that kind of mess around with our understanding of how we can try to make these calculations, well, a common type of heat exchanger is what's usually referred to as a shell and tube heat exchanger. Okay? And in a shell and tube heat exchanger, the whole idea is that we maximize the surface area by taking one of the liquids, usually the one that has the largest density, and flowing it through a series of very small tubes inside of a larger tube that carries the liquid with the lighter density, so like water and air. And so you would imagine that maybe you have a bunch of little tubes. This is a horrible drawing, but again, I'm an engineering professor, not a fine arts professor, so hopefully you'll forgive me. You can imagine that you just have like a bunch of little tubes carrying that liquid that is being exchanged with the other liquid in the larger tube. And of course, the idea behind this is that this maximizes the surface area of contact relative to having just like one large tube that carries the denser liquid. Okay? So this is usually called a shell and tube heat exchanger. You can also have what's usually referred to as a cross-flow heat exchanger. And in this sort of heat exchanger, what happens is that you literally have, maybe you have a single tube, or maybe you have, a bunch of different tubes. So very similar to the setup we had before, except that now the other liquid isn't flowing parallel. Right? Now, the other liquid is flowing perpendicular to the direction of flow of the first liquid, right? Hence the term cross flow. And so here it becomes very difficult because there isn't like a, now we've introduced like two dimensions, right? Because we have that the liquid, the liquid in the tubes is increasing temperature from here to here, whereas the liquid in the in the background, so to speak, is increasing temperature from here to here or here to here, which just makes the analysis of these sorts of systems like extraordinarily difficult from a first principles perspective. Okay? And so you can imagine that there are all kinds of complicated geometries, complicated because of that principle of maximizing surface area, that preclude us from trying to use a simple framework like the one that we've developed here to understand the behavior of the heat in the systems, right, in the exchangers. Which is why understanding and having empirical analyses for what the NTUs are and what the effectivenesses are, and those heat capacity ratios, trying to have empirical understanding of what these things are is incredibly important, because it avoids pitfalls that we would run into if we try to just kind of be very naive about, applying something that is based off of an analysis that it's just a separated tube to something that has such a complex geometry as a shell and tube heat exchanger. Okay? So be aware that this is one of those things that we have to consider in the study of heat exchangers. Now, if we have anything else to say, it's basically to stop and tell ourselves the answer to that last question. What happens if we have that the liquids in a heat exchanger such as this, it doesn't have to be exactly separated by this, it can be a concentric series of tubes where maybe the cold liquid's on the inside and the hot's on the outside, it doesn't matter. For something that's as simple as just like a separated duct with hot and cold liquid flowing through it, we can ask ourselves, is it better to have them co-flowing, that is to say, have them flow in the same direction, versus having them flow in one direction, having the hot liquid flow in one direction, the cold liquid flow in the other? Well, take a look at what you think instinctively would happen to the heat transfer inside of the system as a function of, say, x. Okay? The idea is that we would expect that if both of these things, if this was a co-flow heat exchanger, if the liquids were flowing in the same direction, then you would expect that the temperature of the hot liquid would start off very hot, the temperature of the cold liquid would start off very cold, and then over time, eventually, they would kind of equilibrate into some sort of average or mean value. It doesn't have to exactly be, I'm not saying that it has to be exactly the average of those two temperatures, but I'm just saying that eventually it equilibrates into a single value, right? And then heat transfer stops occurring. this is the intuitive picture of what would occur. And so there is this kind of limit, right, that's set up where the hot liquid at the outlet will inevitably be hotter than the cold liquid at the outlet, and that the cold liquid at the outlet will be colder than the hot liquid at the outlet. And this seems like super easy. Like, this is so obvious. Like, of course, like these are going to be, the hot liquid is still going to be the hot liquid and the cold liquid is still going to be the cold liquid. Like, that makes sense. Imagine what happened if instead now we make the hot liquid come in from the right, okay? So now we set up what's commonly referred to as a counterflow heat exchanger. And whenever we have a counterflow heat exchanger, the idea is that now, from the perspective of this objective coordinate x, okay, now the cold inlet temperature is happening right around here, okay? And so what happens is that when these two liquids kind of meet in the middle, from the perspective of the hot liquid, the cold liquid is just getting colder. And so as a result, that temperature difference increases, or at least doesn't just peter out. And then by extension, the hot liquid becomes colder, right? That more heat is being exchanged from the hot liquid into the cold liquid because the temperature of the cold liquid from the perspective of the hot liquid is getting colder. I know that that sounds like word salad, but just think of it from the perspective of the graph, right? As the liquid starts to hit closer and closer to the cold inlet, of course, the cold liquid is colder. It's closer to its initial temperature. And so you can actually expect that the temperature drop doesn't just peter out. Okay? So maybe it does something like, this. And the same exact thing happens for the cold liquid. Remember, the cold liquid is moving in this direction. So as it hits closer and closer to the left side of the heat exchanger, it starts to see the hot liquid heat up. And so as a result, it receives more and more thermal energy. Or I should say, it continues to receive thermal energy. And so this is, of course, an extraordinarily rudimentary graph of the process via which this occurs. But the key thing that happens is that the hot liquid at the outlet is actually colder than the cold liquid at its outlet. The concept of this being the hot liquid and this being the hot liquid and this being the cold liquid has flipped on itself. And so having a counterflow heat exchanger is almost always better from the perspective of enhancing heat transfer, not only from the fact that you maximize the amount of heat that's actually transferred between the systems, but that you can overcome this barrier where you can actually heat up the cold liquid to the point that it becomes hotter than the hot liquid at the outlet. Okay? It's pretty neat. Now, co-flow heat exchangers and counterflow heat exchangers are the simplest kind of heat exchanger to understand. Usually we don't have to dive deep into the notion of, effectiveness and NTUs whenever we're dealing with a counterflow heat exchanger or a co-flow heat exchanger, at least ones with simple geometry like this, or if it was just a set of concentric tubes. There is one other thing that people like to use to refer to when it comes to characterizing complicated heat exchangers, right? So if we had a heat exchanger that's a cross-flow heat exchanger, right? So flow kind of looks like this for the two liquids. The idea of setting up a 1 and a 2 doesn't really work that much anymore, right? Because this is just an inlet for a cold liquid or a hot liquid. Like, this is just an inlet. This is just an outlet. This is just an outlet. This is just an inlet. So we don't really have the mechanism of just defining a 1 and a 2 over here and then saying, okay, how do we actually calculate these numbers? How do we calculate, for example, delta TLM? Well, what is commonly done is that you'll find that for each of these types of heat exchangers, you create what's called a correction factor F. Okay? And the idea is that for cross-flow heat exchangers and other heat exchangers where you can't really do this 1-2 dichotomy, you basically just say, well, Q is equal to F times U times AS times delta TLM counterflow. And so the whole notion is that you pretend like your complicated heat exchanger behaves like a counterflow heat exchanger. Okay, so you assume that it has kind of this geometry. You work on the problem as if it was a counterflow heat exchanger. You calculate this delta TLM as if it was a counterflow heat exchanger. And then you just have to make sure that when it comes to calculating the Q, you use this correction factor F, which is provided to you by the specs of the actual heat exchanger itself. And so ultimately, this is the kind of paradigm that's associated with calculating properties for heat exchangers in this, standard form of the field of heat transfer and in HVAC systems. And so given that we've done all of this, I think it makes sense for us to now start to dig into examples where we can calculate properties of these heat exchangers as a function of other things. But we'll get to that in the next lecture.